everyone, welcome back. In today's video, we're gonna be solving jump game. So this is a greedy problem, and we're gonna try to solve it with a greedy approach in this case. So let's read the problem. So you're given an array of integers. This is called nums, and you're initially positioned at the first index of the array. Each element represents your maximum jump length at that position. You have to return true whether we can reach the last index or false otherwise. So basically, if we have an array such as 2, 3, 1, 1, 4, we'll first be here at index number 0. And from this element, we can make two different jumps. We can either make a jump of length 1 to the index number 1 of length equals 1, or we can make another jump of length equals 2 to this element right here, to this 1 right here. And so basically we have to keep doing these jumps until we reach the end. If we can reach the end, then we can say that this will work, therefore we'll return true, otherwise it will return false. So that's kind of like the idea, right? So now let's look at the example more in depth. So I'm just going to go down right here and copy the example that we had. So basically, let's suppose we have this array, 2, 3, 1, 1, 4, and from here, you can sort of think it as a tree, right? I mean, if we're at element number 2, we can either make a jump of 1 to this element right here, to the 3, or we can make another jump to this element right here, to this 1 right here, of length number 2. Now, once we're at this 3 right here, then we just keep expanding the tree. So we're at 3, we can make a jump of length 1 to your 1 right here. We can either make another jump of length 2 to the other 1, so this one right here. And finally, we can make another jump of length number 3 to the 4. Notice how we just solved the problem, right? We just expanded this tree, and we found that by following this path, by first going to this 2, and then going to this 3, and then going to this 4, we're able to reach the end. So in this case, in this example, this will return true because we were able to get to the last index of the array using these jumps. So basically, one could think, well, this is easily a backtracking problem, right? I mean, at the end of the day, we have a tree. You just have to keep looking for options until we find the solution, right? But basically the main problem with this approach is that we have a tree of n levels, and at each level, at each number, we can jump up to n places, where n is the length of the array. So at the end of the day, since we have n levels, and for each level we can jump to up to n places, we have a complexity of n to the n. This is quite bad. This is exponential, and if you look here at the constraints, we can see that n will go quickly, very high, very quickly. So for instance, here we're gonna have 10 to the 4, which is very, very high, and using this complexity, it won't end well. We'll definitely get a TLE if we try to do it this way. So we have to be smart in that, and we have to come up with a better solution. And I think like one way of doing this, which would be better, would be to like think about where we start making this, where we start originally and where we want to end. So let's assume now that we are at the last element, right? And we are at 4. If we are at 4 originally, what we can do is we can simply say, okay, well, what happens if, so I guess the main idea here is, can I jump to 4 from another element, right? Because at the end of the day, I want to get to 4. So I'm going to check now the previous element. Okay, can I make it to 4 from this 1? Yes, I can, because this allows me to jump 1 place. So now the new target, we simply move it, right? Because we've established that if we get to this guy, we can make it to the end. So therefore, we want to see if we can now get to the previous element. So we simply do that again. So we say, okay, what about the previous element? Can I get from here, from this element to here? Yes, I can, because this is length 1 as well. So therefore, we move the pointer again, and we say, okay, now we are here. Okay, so I want to get to this element right here. okay, can I do it for my previous guy? Yes, I can. This allows me to jump up to 3 places. Therefore, I can either jump here, here, or here. Okay, so I just move the pointer again, and this is now the new target. This is where we want to reach again. And then I say, okay, can I reach this element from this guy, from the previous guy? Yes, I can, because the distance is 2, so I can either jump here or here. And therefore, the 2 is the new target, right? But since we've established that we're starting from the first index, then we say, okay, we can actually reach the end, because we can reach this 2. Sorry, from here we can reach the 4. From here we can reach this guy, and this is good because from here we know that we can also reach this guy, so that works out for us. Then we say, okay, from this guy we can reach this guy. And lastly, if this guy works and leads us to the solution, that means that we have to get to this guy, and since we can get to this guy from the index number 0, then that means we can actually get to the solution. So this is how this would work. This is a greedy approach. Basically, we will start at the end and simply keep checking for the previous element and see whether we can actually reach the current element from a previous element. So let's look at a more complex example and see if we can actually make it work. So this is the example number 2. We're going to have 3, 2, 1, 0, 4. Okay, so we're going to be here at the last element, as always. From here we say, okay, can I reach this 4 from anywhere? I go check this guy. This is 0. This means that once I'm here, I'm stuck forever. I cannot make any kind of jump, so this is useless. Let's look at the other example. Okay, from this guy, well, this only allows me to jump 1 place, so yeah, that doesn't really work. Let's look at this other guy. From this guy, I can make 2 jumps. I can either go here, but we established that this is not the target, therefore that does not work. Or I can go here, and also this doesn't work because I'm stuck here, so no, we cannot go here. And lastly, if you look at this guy, can I go to 4 from this guy? Well, I can either go to 2, go to 1, or go to 0. So therefore, since our target is 4 still, is this element right here, and this is different than 0, we can just return false, because there's no way we can actually reach the end of the array, right? So that's sort of the idea, right? This is going to be an edge case. And I guess something that's important to note is that we're going to be moving this target as we go, because once we've established that we can reach a certain number, that means we have to move it around and then check for the previous element for that target. So now let's come up with the solution in Python code and let's discuss it. Okay, so let's finally come up with the programming solution for this problem. So I'm going to start with an example. So let's say we have 2, 3, 1, 1, 4. And from the previous approach, we have established that we want to start at the last index of the array, right? So the target element, the element I want to get to, is going to be target line of nums -1. Why -1? Because remember that here, right, we have 1, 2, 3, 4, 5 elements, so len of nums is going to be 5. But since I want to be here, right, in Python, indexes start at 0, so this is going to be 0, 1, 2, 3, 4. So this is why I'm subtracting 1. That way we guarantee that we are here. Okay, now once we are at the last element, I want to reverse the array, right? I want to start from the previous guy and check whether I can actually make it to the target or not, right? So once we are here, I want to see, okay, well, can I reach my 4 from this guy, right? So we have to reverse the array. So I'm just gonna say for I in range of target -1, this -1 is because I want to check the previous guy, right? The previous guy from target. And I'm going to decrement by -1 each time and also stop at -1. Remember that in Python, all loops, they finish at, so they're not inclusive. That means that if I put here -1, this means that it will stop at 0 and not at -1. And so once this is done, I want to now compute the distance, right? If I'm at my 1 right here, right, I want to see, okay, well, what's the distance between 4, my target, and my current guy, right? In this case, this would be 1, right? So I'm going to just say distance target minus I. So this will compute the distance between my current element and my target. So once we have the distance, I'm going to say, well, if I, from I to 4, I have a distance of 1, well, this I allow me to jump 1 place. So I'm just going to say, okay, if distance is smaller or equal to nums of I, in other words, if I can make it to, if I can jump as many elements as distance, then we'll just say, okay, well, we can actually make the jump, right? I mean, if this between 1 and 4 is 1, and here this element is allowing me to jump 1 place, then of course we can make the jump, right? So then we have established that if we're at I, we can reach 4, right? So in this case, then I'll say, okay, well, I want to check now from this one right here, I want to check if I can reach this element from a previous element, right? So I'm going to I'm going to swap the target. I'm just going to say target equals I. And so this process will be repeated until we finally reach the end, right? Because we're going to check, okay, well, from this guy right here, can I reach this guy right here? Yes, I can, because the distance is 1. Okay, awesome. Once this target is right here, once target is the first one, then I will ask myself, okay, can I reach this one from 3? Yes, I can, because the distance again is 1 and this is 3. It allows me to jump up to 3 places, so therefore I can afford to make the jump, right? I can do it. Then lastly, 3 will be our target, and as we're at 3, then we will check, okay, can I jump from the previous guy from 2 up to 3? Yes, I can, because the distance again is 1, and this allows me to make a jump of 2 up to 2 elements, right? So I'll swap it again, and eventually we'll have a target equal to 0. Once this is the case, that means that we were able to traverse the array from the last guy up to here, right? And that means that we can just return true, because we were able to make the jump, right? So I'm just going to say, well, if target is equal to 0, then we'll simply return true, because this condition will be true. It will satisfy. And then if this is not true, if target is not equal to 0, that means that after reversing the entire array, we were not able to reach the first index, and therefore there is no path. We can guarantee that there won't be a path from this guy to here. Okay, so let's look at the proof now. Let's submit it. And there we go. It beat 64% of the solutions, and yeah, it works pretty well. Now let's look at the runtime complexity real quick. So let me go back to the problem. Notice that at the worst case scenario, we're always traversing the entire array, right? We're only passing through once. If there's an element in our array, right, this would be O of n, because it's a simple for loop. So the runtime complexity is going to be O of n. Okay, thank you so much for watching the video. I hope this was helpful, and I'll see you on the next one.